All right, so I've mentioned this before, but this is kind of the big picture for star formation. So just kind of, go through it here. One, thermal energy escapes from the interior of a protostar and is radiated into space. The protostar contracts. A protostar's luminosity comes from gravitational collapse. It's converting gravitational potential energy into thermal and radiation. If it's contracting slowly, then we can apply the virial theorem. It's almost in equilibrium. It's in quasi-equilibrium. And so in that case, what fraction of the gravitational potential energy is being converted into thermal energy, heating up the protostar, and what fraction is being radiated away? What's the balance there? Do you remember from the virial theorem? It's, what is it? What is it? Half and half, yeah, it's 50-50. Half of it's radiated away, half of it is converted into thermal energy. So gravity is very slightly winning the battle after an initial free fall period. When it becomes optically thick, then you get almost into balance between pressure and gravity because it can trap its own radiation. And as a result, the interior is able to start heating up. As a result of that, gravity is stronger in the smaller protostar, pushing up pressure and temperature. The cycle continues. As the protostar gets smaller and smaller, its interior gets hotter and hotter. In this way, the protostar's gravitational energy is converted into thermal energy and radiation, not mentioned here, until the core gets so hot that hydrogen fusion begins. Hydrogen begins fusing into helium at a temperature of, what's the ignition point for the proton-proton chain? Do you remember? Roughly speaking, how many glorious Kelvin initiates hydrogen fusion? What's the ignition point for that? Yes?
10 million?
About 10 million Kelvin, yeah. So if the interior hits 10 million Kelvin, then hydrogen fusion begins, and that's when we can get a long-term equilibrium between the pressure in the core and the weight of the overlying layers. It goes throughout the star, but in other words, when there's thermonuclear power being created in the star's core, then the new star settles down into its main sequence life, beginning burning hydrogen in its core. So does anybody happen to remember what's the minimum mass of, what's the minimum mass of a protostar, basically, something that's going to turn into a star, in terms of the mass of Jupiter? Yes? About 80 Jupiter masses, whereas the sun has about how many Jupiter masses? About 1,000 as a matter of fact, yep. So in other words, anything from about 8% of the mass of the sun and above is enough to turn into a star. If it's on that end of things, it's just going to be a cute little red dwarf that's going to live for hundreds of billions, maybe even more than 1 trillion years, because it burns its fuel at such a leisurely pace, even though it doesn't have nearly as much as the sun does, that whole story. But that's what we need. So greater than 80 solar masses, you get yourself a star. What happens if we are between about 13, I should say, and 80 Jupiter masses? What do we call it in that case? Why, it doesn't make a star and it doesn't make a planet. It makes a brown dwarf. It makes a brown dwarf. Brown dwarf. And what is it that distinguishes a brown dwarf from a planet? What would make something 12 Jupiter masses a planet, whereas something with 13 Jupiter masses is a brown dwarf? What's the distinction? Yes?
It's burning deuterium.
Yeah, it fuses deuterium for a little while. Undergoes a brief, because there isn't a whole lot of deuterium there, period of deuterium fusion into helium. full-fledged stars do this too, but with a brown dwarf, it never gets past this stage. And that happens when the core temperature is about 1,000,000 Kelvin. But if it's less than 80 Jupiter masses, it doesn't get to the point of 10 million Kelvin. The core never gets that hot, and so it never gets past a brief period of deuterium fusion. And then less than 13 Jupiter masses, degeneracy pressure kicks in within the core before it reaches a temperature high enough for deuterium fusion. Deuterium pressure starts supporting the core before it gets hot enough to fuse deuterium. So it never does, because the degeneracy pressure makes it stable. Remember, deuterium is 21H, proton plus neutron in the nucleus, so two particles, one proton makes it a hydrogen. And so those are our scenarios. So if degeneracy pressure kicks in, then it's never going to be a star, because it just becomes stable, supported by degeneracy pressure. As we'll see past chapter 13, when a low mass star dies, it ends up as a white dwarf, which is supported by degeneracy pressure, as a matter of fact. But that comes much later for a full-fledged star, and we're talking more like, could be more like half the mass of the sun, up to about 1.4 times the mass of the sun. In that case, it's a much more massive object, but only about the size of Earth, smaller than something with this mass, because it'll be of a radius more like comparable to Jupiter. Okay, what questions do you have? Wait for folks to catch up in writing there. Guess I'll go back to the decorative picture. All right, so we talked about giant molecular clouds colliding with one another. Magnetic fields within the clouds play a role in that, because if the temperature in a region where they've collided with one another gets hot enough to produce some ionization, then charged particles have to move along magnetic field lines, shown as pink here. So maybe you've studied before motion of a charged particle in a magnetic field. Remember that the force is QV cross B, and that produces, it can produce just uniform circular motion in a uniform magnetic field, but in general, it causes particles to spin around the field line, so to speak, spiral around the field lines, and then so that traps them on the field lines, if you will. But then there's also collisions with neutral particles, atoms, and so forth, and that transfers momentum, and it inhibits, in general, motion perpendicular to the field lines. And so the magnetic field, as a result of this, helps the cloud to resist gravitational contraction. So a magnetic field plays a role in producing so-called magnetic pressure that can help support a cloud against gravity. And it also helps colliding molecular clouds kind of push on one another better, because it resists having them simply pass through one another. What questions do you have? All right, so here's a simulation, a computer simulation of a cloud forming stars. So we've talked before about the Jeans mass, right, last time. And we took a simple model where you had a spherical cloud that if its mass is greater than the Jeans mass, gravity will exceed pressure. And then we assumed it just nice and gently collapses as, well, not gently at first, but eventually collapses, maintaining its spherical shape, and produces a star. But reality is more complicated than that, because there's turbulence within an interstellar cloud, and as a result of that, they tend to break apart when they're collapsing. So here we've got a turbulent gas cloud that starts out 1.2 light years across, containing 50 solar masses of gas. Random motions within the cloud, the turbulence, cause it to become lumpy, with some regions denser than others. If gravity can overcome thermal pressure in these dense regions, in other words, if they exceed locally the gene's mass, they can collapse to form even denser lumps of matter. And so what happens then is you get fragmentation, where you form multiple stars from a cloud, where you form potentially an entire cluster of stars from a cloud because of fragmentation during the collapse process. Now, one mystery for a long time was, where is population 3 stars? So population 1 stars, pop 1, population Roman numeral 1, those are, I guess I should turn the camera towards what I'm writing on the board. I should hire you folks to be camera people. All right, there we go. Population 1. Galactic disk stars. Stars in the disk of our galaxy, and presumably other galaxies as well. And these have a large range of ages, because star formation is still happening within the galactic disk, right? We see age 2 regions. Those are stars being born now. Large range of ages, because star formation still active. And that means that the ISM, the interstellar material in the disk, has been enriched in metals. What's a metal to an astronomer? Except, right, if it ain't hydrogen and it ain't helium, it's a metal to an astronomer. So the ISM has been enriched in metals. By generations of stars. And so that means that Pop 1 stars have relatively high metallicities. %2 by mass would be pretty typical. That's like the sun. But some up to 4% by mass is what I've seen for metallicities. That's population 1. I'm going to zoom out some more so that I don't have to erase that. Then there's population 2. Oh, so well, okay, I'll write this first and then I'll ask the question. Halo stars, stars in the galactic halo above and below the disk, spherical distribution above and below the disk. many in what we call globular clusters, which we'll talk about next chapter more so. Very old. Because they formed early and there is no ongoing star formation in the halo. It already used up the gas and dust. It already used up the gas, really. So if those stars form very early, should they have high metallicities or low metallicities? They should have low metallicities because there wasn't as much time for the interstellar material to be enriched by prior generations of stars. They're very low metallicities. Population 3, that would be the first generation of stars. Where do metals come from? Stars. So if you're in the first generation of stars, what's your metallicity? Essentially 0. There'd be a tiny little bit of lithium left over from the Big Bang, but essentially 0. No prior metal enrichment of ISM. Metallicity should basically be 0. So what are they made of? Hydrogen and helium. Pure H and He composition. That's a little bit of a lie. Tiny amount of lithium from the Big Bang. Big Bang made a little bit of lithium, and I forget, it made something else too, but it'd be a little lithium, a little bit of deuterium. Well, that's a type of hydrogen. Essentially, they're made of pure hydrogen and helium, and never been observed. Population 3 is hypothetical. It's never been observed. Bit of a mystery. Why have we never seen any stars that are made of nothing but hydrogen and helium? Well, we think we know the answer now. So here it is. Remember how we said that the way that we observe giant molecular clouds with our radio telescopes isn't to look for radio waves being emitted by molecular hydrogen. Instead, we look for radio waves emitted by molecules like carbon monoxide. Why was that again? What's the problem with hydrogen, a hydrogen molecule, in terms of it emitting radio waves by vibrating or rotating, as it were? Yes. It's not polar. You need charge separation. You need it to be dipoles in order to emit dipole radiation, to emit radiation due to the quantum mechanical version of vibrating and rotating. So as a result, molecular hydrogen, which is not a polar molecule because it's symmetric, is terrible at emitting radio waves. And Kathleen cannot read what I wrote. Let's see.
What's the word before H?
Oh, pure, oh, pusé, pure,
Okay.
pure.
It looks like PUP.
Okay, that would be pure,
Thank you.
pure hydrogen and helium composition with a tiny amount of lithium from the Big Bang. Never been observed down there, which would be kind of nice if that was illegible, because then you wouldn't be able to observe that they had never been observed. But in any case, so here's the thing: if we can observe radio waves, and for that matter, infrared radiation, because there's also infrared radiation emitted by polar molecules like CO. That means that that's a means for the cloud to cool. That's a means for the cloud to radiate thermal energy. And so a cloud with polar molecules in it will be cooler in temperature than one that does not have polar molecules in it. And thus we get to this scenario. The earliest stars, the hypothetical, probably existed. Have to have existed. They have to have existed. The earliest stars formed from clouds made only of hydrogen and helium with no polar molecules like CO to cool them. The cloud would stay warmer, and if you look at our formula for the Jeans mass, it's got the temperature in it. It would have a higher Jeans mass as a result of that, because those stars, if it stays warmer, what's that going to do to the pressure? Is it going to make it larger or smaller? All else equal, it's going to make it larger. And if the pressure is larger, it's going to make it harder for gravity to win the battle between pressure and gravity. It's going to increase the mass the cloud would need in order to collapse. So the Jeans mass would be larger, and that would explain why we don't see those stars. We don't see any stars with essentially no heavy elements in them at all. The first generation of stars would have all been very, very massive. And what do we know about the lifetimes of massive stars? Very small. So in other words, they would have all blown up good very quickly, leaving no remnant other than the fact that they helped seed the interstellar medium with an initial enrichment of metals. And so that appears to be why we don't see any population 3 stars, because the fact that there was the clouds that would have formed them wouldn't have been able to cool off due to polar molecules, would have forced them to be very massive, like 100, 200 times the mass of the sun. The Jeans mass would have been very large. And so they just went off like fireworks very early. The first round of star formation in the universe was like boom, 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 lots and lots of supernovae. And they just very quickly destroyed themselves, and so we don't see them anymore. To see them now, we would need to have very low mass ones that would live longer than the current age of the universe, and they wouldn't have existed. They wouldn't have formed. Does that make sense? That's the idea there. What questions do you have? Okay, that's the story there. This is a plot of what's called the initial mass function, the IMF. Folks that are studying star formation, they're very interested in what fraction of stars form with a given range of masses. And then this would feed into, well, how many stars of different masses do we see now? It's going to certainly be directly tied into the rate at which they're formed. And the answer is observationally, and this is something that theorists want to try to explain, observationally, there is a strong tendency to have fragmentation of collapsing clouds so that stars of smaller masses form more readily than stars of larger masses. So here's a very here's a very unevenly binned histogram, where if we go, okay, 261 stars, I guess, so to speak, right, if you add them up, relative number of stars here, 261, of every 261 stars, roughly, this isn't exact, right? So why 200 of them are with masses between 0.08 times the sun's mass and half the sun's mass. What's magic about 0.08 times the sun's mass? That's the lower limit. No, Jupiter is 0.001. Yeah, this is the 80 Jupiters is 0.08 solar masses. That's the lower limit for a star to be a star in the first place. So 200 of them are less than half the sun's mass. And as this kind of illustrates, it's actually, it's even more so the lowest mass ones. The most common type of stars are red dwarfs. Those are the most common type of star. You can't tell that from looking out in the night sky because not a single red dwarf is visible to the naked eye. They are so puny, relatively speaking, in terms of the amount of light that they give off, that even though the nearest star is a red dwarf, it's below naked eye visibility. Proxima Centauri is the nearest star to Earth. We can't see it with the naked eye. 50 stars between half and 2 solar masses, 10 stars between 2 and 10, between 10 and 150, just 1. So, in other words, the highest mass stars are actually quite rare, and yet they produce a substantial fraction of the light of a spiral galaxy, because each one of them can be like 50,000 or 100,000 or more times the sun's luminosity. So they're very rare, but they're very loud. And so that's why the spiral arms of spiral galaxies look blue, because the very rare O and B type stars emit so much light that they end up dominating the light of the spiral arms. But if you photograph a spiral galaxy through a filter that doesn't let through blue light, it's hard to see the spiral arms. The stars that are lower mass are more evenly distributed. Yes?
I saw somewhere that the red giants are more massive, but they just larger.
So the red giants can be low mass stars that have gone, that have used up their central hydrogen. They are physically bigger in diameter. They're much more luminous. The sun will be about, when it's a red giant, when it's a red giant the first time, it'll happen twice, it'll be about 2,000 times more luminous than it is now at its brightest. When it's a red giant the second time, a so-called asymptotic giant branch star, say that 10 times quickly, it'll get to about 5,000 times its present luminosity. And it'll be like 100 times bigger across than it is now. But it's still, you'll have less mass than it does now because it'll have blown off some of its mass. Because when it's a red giant, it won't be holding on to its outer layers very tightly, and so it'll have a strong stellar wind as a result of that. Does that answer your question?
Yeah.
Yeah. Mm-hmm. Yep. Here we're just talking about the masses that they form with. So this, again, you'll so often hear the sun is an average star, it's an ordinary star, blah, blah, blah. But that's deceptive because the sun is roughly in the 90th percentile. The sun is actually a big star as they go. It's more massive than about 90% of the stars in the universe. Now, it is vastly outshone by stars that are more massive than it is, ones that are like, the ones that are 10, 50, whatever times the sun's mass are spectacularly more luminous. But the sun it's up there. We call it a medium-sized star, but if you look in terms of the percentile, no, it's a big star. It's more massive than most stars are, and more luminous than most stars are. Something to be aware of. Okay, so let's see. Well, I'll just read this. So here, what do we call this band right here? In the HR diagram, that would be the main sequence, and stars that are on the main sequence, where are they getting their energy, and where is it happening? Hydrogen is fusing into helium in the core, right, in the core. Here is a kind of a stylized 1 solar mass protostar evolutionary track, we say, right? The evolutionary track is the path that the point that represents a star follows on the HR diagram. So, 1, a protostar assembles from a collapsing cloud fragment. It is concealed beneath a shroud of dusty gas. We sometimes call that its cocoon, which is kind of a fun name. The protostar shrinks and heats as gravitational potential energy is converted into thermal energy, and also It's converted into thermal energy and in a 50-50 mix, thermal energy and radiation, yes. So it is powered by powered by glue, that's correct. Yes. Gravity, yes, it's powered by gravity. Significantly more luminous was the sun as a protostar than it is as a full-fledged star now when it was gravity powered. Gravity power can be quite efficient. And so this represents the period, the point at which it is slowly contracting, releasing gravitational potential energy, converting it into thermal energy and radiation at this point. And it slowly but surely settles onto the main sequence when the core temperature finally reaches what value? About 10 million Kelvin, about 10 million Kelvin. Just as high mass stars burn through their fuel more quickly and don't spend as long on the main sequence, they also collapse more quickly and take less time to reach the main sequence from the protostar stage. And so here are some protostar evolutionary tracks labeled with, according to computer models, how long it takes the protostar to complete its collapse to form a zero-age main sequence star. And so you can see for the sun, it's roughly 30 million years. Now, let's see, how long will the sun be on the main sequence, roughly speaking? 10, what's the next letter before the illion? It's a B, yeah, about 10 billion years, right? 10 billion years. 1 million is what fraction of 1 billion? 1,000, right? 1,000 times a million is a billion, right? So 30 million years is what? 30 million years is like one. If the sun lived 30 billion years on the main sequence, this would only be 1/1000th of that. Well, it's more like 10 billion years, so it's like 1/300th of that, right? So the sun took only about 1/300th as long to collapse to reach the main sequence as it will spend on the main sequence, right? So keep that in mind. A star spends much more time on the main sequence than it does actually in any other stage of its life, as we'll see. The vast majority of a star's lifetime is spent fusing hydrogen into helium in its core in the main sequence. This becomes relevant later when we talk about using HR diagrams of clusters to determine their ages, and we can assume that they were all born at essentially the same time, and part of that is that the time it takes stars to be born is a tiny fraction of how long they spend on the main sequence. And so that means that it's a decent approximation to say they all formed at the same time. For a star 3 times the mass of the sun, it takes more like 3 million years to reach the main sequence from the protostar stage. 9 solar masses, 150,000 years. 15 solar masses, 60,000 years. I mean, set your watch. Okay, well, don't set your watch, but still, 60,000 years is nothing, right, astronomically speaking. Half the sun's mass, 150 million years. But then this brings up something interesting. Wait a minute. If you have a star that's like 15 solar masses, you've got a cluster of stars forming, like in an H2 region. Okay? If they all started collapsing at the same time, then the 15 solar mass star would collapse in 60,000 years. How long would it take to blow itself up? I don't need an exact number, but would it be a few million years, a few billion years? Roughly speaking, what are we talking here for a 15 solar mass star? How long does it spend on the main sequence? A few million years or a few billion years? A few million years. It spends a few million years on the main sequence, which is less time than a star like the sun takes to form in the first place, and much less time than a star half the sun's mass takes to form in the first place. So in other words, the most massive stars in a forming cluster can blow up and be gone before the lowest mass stars have even fully formed yet. So that's something to keep in mind. Here is a photo of the Orion Nebula, which shows circumstellar disks within it. So these are, here's like an infrared photo. The star's light in the infrared can shine through the disk. Here's the size of our solar system, quote unquote, well, as defined by the orbit of Pluto. That's not really the size of our solar system per se, but in other words, these disks are about the right size to be where planets would be forming around the stars. And in fact, that is where planets form, is within disks around protostars. So why would a disk form around a protostar? So you've got this material falling in, and as the gas cloud collapses, it should essentially conserve angular momentum as long as there's not a lot of torque being exerted on it from the outside. So it conserves angular momentum, and it's also shrinking. So what's happening to its moment of inertia as it shrinks? Do you remember, how do you define the moment of inertia? I mean, there's various formulas, but what's the definition of the moment of inertia? Do you remember? So well, okay. When is my moment, if I'm going to spin around a vertical axis, when's my moment of inertia larger? Now or now? Was it bigger here or bigger here? First one or second one? Yeah, when I was more spread out. The moment of inertia around a given axis of rotation is you add up, if you think of it as like all atoms if you want, you would take sum of the MI/RI squared, where RI is the distance from the axis of rotation. So add up mass times distance from the axis of rotation squared. That's the moment of inertia. So for a person, you could think of it as like, take every atom and multiply the mass of the atom times the distance squared from the axis of rotation. That's the moment of inertia around that axis. So clearly, if you're more spread out, you've got a larger moment of inertia because you've got more atoms further from your axis of rotation. Did Dr. Trees or anybody else ever do the demo for you where you bring the arms in, right? That's why it's the Winter Olympics. What sport does this especially apply to? Ice skating, right, yeah. A skater spins faster when they bring in their arms because they're reducing their moment of inertia. But there's not a lot of friction with the ice. That's the point of it. And so therefore, that plus the fact that they do it quickly means that their angular momentum stays the same. And since the angular momentum is the moment of inertia times the angular speed of rotation, right? I omega, if I goes down, omega has to go up. Well, this applies to a collapsing protostar as well, right? The cloud is shrinking. What's happening to its moment of inertia? It's going down, so what better be happening to its angular rotation rate? It's going up, yeah. So the cloud spins faster as it collapses, and intuitively, you can understand why that means, you can put more math behind this, but that means it's easier for material to collapse along the axis of rotation than it is perpendicular to the axis of rotation. And if you want to visualize why imagine, I've been saying this with the, okay. Hello, people at home, okay? If you want to imagine why, okay, imagine that you're holding some weights and your job is to pull them in towards yourself at the same time that you're spinning around. Scenario A, I'm going to try to pull the weights in. Scenario B, I'm going to try to pull the weights in. And ignore Earth's gravity. I'm not talking about the fact that if I let go, it'll bonk me in the head, right? Maybe knock some sense into me or whatever, right? Ignore that. I'm in outer space here. I can't breathe. Oh, no, okay. So I'm not, oh wait, here, I'll put my spacesuit on. I'm fine now, okay? Intuitively, what's going to be easier? pulling weights in when I'm spinning and trying to do this, or pulling weights in and I'm just trying to move them along my axis of rotation? Which is easier? Definitely along your axis of rotation, right? It's definitely easier to do that. That's true for a collapsing interstellar cloud as well. It's easier for material to collapse along the axis of rotation than it is perpendicular to the axis of rotation, essentially because of quote-unquote centrifugal force, if you will. If you go into a rotating frame of reference where you can talk about centrifugal force that appears to fling things outwards, you have to overcome that in order to bring material in a direction perpendicular to the axis of rotation. And so a collapsing interstellar cloud flattens into a disk at the same time that it's shrinking and rotating faster and faster. And so as a result, a disk of material forms around the protostar. Most of the material by far is in the protostar, but there's a substantial amount of material in a disk surrounding the protostar. And interstellar clouds contain a little bit of dust in addition to gas. And that dust is good at scattering light, at making it hard to see through the disk. And so that's why we get these scenarios like this, where here we're seeing this disk edge on. You can't even see the star because it's become optically thick because of the dust in the disk, not allowing photons to travel very far before they hit a dust particle. Here's a disk seen from above where we can more readily see the protostar forming inside. And so in other words, theoretically, disks, protostellar disks, or really we can even say protoplanetary disks, should form around collapsing protostars. And observationally, we see them. Here are protoplanetary / protostellar disks around collapsing stars. This is why all the planets around the sun are orbiting in very nearly the same plane. Does anybody know, what do you call that plane? What do you call the projection of Earth's orbit onto the celestial sphere, meaning the projection of Earth's orbital plane around the sun onto the sky, onto the celestial sphere? Does anybody know, what do we call that? It starts with an E. It's the, not the equator. That's the projection of Earth's equator onto the celestial sphere. You look like you want to say it. No, that's the shape of the orbit. EC, the ecliptic. The ecliptic is Earth's orbit projected onto the sky. It's called the ecliptic because for there to be eclipses, the moon also has to be on the ecliptic. And so it gets that name from that reason. All the planets that we look, when we see planets in the sky, they're always within a few degrees of the ecliptic. And the reason is because their orbital planes are tipped no more than a few degrees relative to Earth's orbital plane. All the planets, to a good approximation, orbit the sun in very nearly the same plane that Earth does, and they all go around the sun in the same direction. This has a natural explanation. They formed in the protoplanetary disk around our young sun. And as a result, the fact that they do this, they are in the plane of that disk. The plane of the protoplanetary disk is the plane that the planets are orbiting in now. That's a little too strong a sense because it's not a single plane, but in other words, they're very nearly in the same plane because they formed in a disk. They're going around the sun in the same direction, the direction that disk was orbiting the sun. So this is why the solar system has that overall property. Ooh. Ah. Okay. Questions, comments, observations? And here we see it happening in other stars as well. Yes?
So if you have a bunch of stars forming and you have massive stars forming, then does that affect the formation of the other stars?
It can, yeah. So if you have a star forming region and you've got massive stars forming and blowing up good, because that's what they do, they blow up a supernovae, can that affect the formation of other stars? Yeah, the answer is it can. So first of all, remember that strong stellar winds from those stars can actually help to initiate star formation in other parts of the cloud. A supernova shockwave can help to initiate star formation in nearby parts of a cloud. But at the same time, winds from stars and supernova shockwaves can blow away material. There's a very famous Hubble Space Telescope photograph of, I guess it's the Eagle Nebula, where they call it the Pillars of Creation. And they have what they call EGGs in there, evaporating gaseous globules. The pillars are being destroyed by winds from hot stars that are forming nearby. And so it can go either way. Hot stars can help seed additional star formation, but they can also terminate star formation near them too by blowing the material away. So it kind of, depends on the particular conditions which effect is more important. So the answer to your question is yes, it can definitely affect it. Yep. What other questions do you have? Yes?
So is it difficult for planets to form these disks, or are planetary systems like common?
Well, yeah, we used to only be able to speculate, but now with ground-based and space-based planet hunting missions, the answer seems to be, yeah, it's easy. Planet formation is very common. A very large fraction of stars appears to have planets. What's interesting is we've got enough statistics now to say that our solar system is probably unusual in that we have terrestrial planets close in and at a pretty good separation from them, Jovian planets further out. And there are many planetary systems where the planets are much closer together than they are in ours, or where Jovian planets are close to the star. And so it seems to have been special conditions that in our solar system managed to keep Jupiter and Saturn at nice distances. So there's good Jupiters and bad Jupiters, if by good you mean helping life form within the system or getting in the way of it, and we have a good Jupiter. It's thought, and there's computer models that back this idea up, that Jupiter, a planet like Jupiter, interacting with leftover material in the disk can create a sort of drag on it that causes the planet to migrate inwards. And that can be a disaster in terms of if Jupiter had migrated inwards far enough, well, that would have disrupted the orbit of Earth, Mars, Venus, and so forth. But Jupiter, with its larger mass, would have formed first, started wandering in. One model I've seen, it starts wandering inwards, but then Saturn forms and gives Jupiter a tug and pulls it back out and stabilizes things so that we're having this conversation. And so when you see Jupiter and Saturn, you might thank Jupiter for allowing there to not be as many cometary impacts as there would otherwise be, threatening our survival, for not wandering into the inner solar system and ejecting the terrestrial planets. And then you thank Saturn for keeping Jupiter under control. I think it's fascinating. Again, one thing that I get asked sometimes by people is, why do you care about this stuff, right? You're never going to go there. What's it have to do with your life? And I'm like, well, the fact that I exist, for one thing, the fact that you exist, right? I mean, I'm preaching to the choir here, but I think it's interesting to learn things about the kinds of conditions that were necessary for people to say stupid things like, why do you care about the rest of the universe? How does it affect your life, right? So anyway, time for a break. We'll end there for now. All right, let's kill some stars. Seems kind of mean, doesn't it? And yet, nothing lives forever, including our own beloved sun. So prepare now. You've only got about 5 billion years before the sun starts swelling up into a red giant. But as we'll see, long before then, in more like 1 billion years or so, Earth will become uninhabitable unless our distant robot descendants do something about it, or whatever our distant descendants are. Yeah, I was watching the Super Bowl yesterday, and there's this commercial. It's like, AGI is coming, and I'm like, am I supposed to be excited about that? Because I'm not. But anyway, it was fascinating to think about it, but I don't know, all the science fiction movies are like, it's never good for humanity when we get machines that are smarter than us showing up. I don't know. Anyway, on to this. So, I already mentioned this, but let's go through it again here. The sun today is larger and brighter than it was when it first reached the main sequence, when it was on the ZAMS, the zero-age main sequence. It's something like only 60% its current luminosity when it first became a main sequence star, first got hot enough to fuse hydrogen into helium in its core. Here's a comparison of the sun 4.6 billion years ago and the sun today. The size is supposed to be accurate. The size comparison was the brightness comparison. Well, that's obviously just it's just kind of illustrating the idea that it was dimmer and cooler back then. Why? Why was it dimmer and cooler? The sun's luminosity, effective surface temperature, and radius are all slowly increasing during its main sequence lifetime because hydrogen burning is increasing the value of mu, the mean molecular weight in the core. Put another way, it's reducing the number of particles because 4 hydrogens produce a single helium nucleus. And so the number of particles, which is what shows up in the ideal gas law, right? The pressure is the number density times K times T. It doesn't matter what the particles are. All that it matters is how many of those particles there are per cubic meter. So if you're changing 4 hydrogens into 1 helium all the time, you're reducing the number density in the sun's core, and that in and of itself would lower the pressure if nothing else changed to compensate. So what this means then, by the way, is that the main sequence is not just a thin line on the HR diagram. It has some width to it because stars do change in luminosity and surface temperature while they're still in the main sequence. So the main sequence, even from a theoretical standpoint, is a narrow band on the HR diagram. It's not a thin line on the HR diagram. Since P equals rho KT over mu MH, as we've gone over before, right? Because rho over mu MH is kilograms per cubic meter over the average mass per particle. So rho over mu MH is the number density, little n. Since P is rho KT over mu MH, rho and or T has to increase to maintain sufficient pressure to support the weight of the overlying layers. And as a result, the core is compressed, rho increases, and by the virial theorem, T is increasing also, because if the core is shrinking, then it's converting gravitational potential energy to thermal energy. So the sun's core is slowly heating up while it's on the main sequence because of the ongoing fusion, reducing the number of particles there. In other words, it's not in a perfect balance between gravity and pressure. Gravity is always a little stronger than pressure in the sun's core, only a little, but over long time scales, it's slowly increasing the temperature of the sun's core in order to maintain being close to equilibrium. Since the PP chain nuclear reaction rate goes like as we saw in what is now 2 chapters ago, chapter 10, goes like rho x squared, where x is the hydrogen mass fraction, T6 to the 4th power, then the nuclear energy generation rate is increasing because x is going down as you convert hydrogen into helium, but T to the 4th is a bigger factor here. The increase in temperature is a bigger factor, and so the nuclear reaction rate is increasing because of the temperature increase in the sun's core. So the sun's luminosity is increased by something like 40%, and its radius by something like 6%, and its effective temperature by something like 300 Kelvin since it arrived on the main sequence. So that means that when it was a ZAMS star, zero-age main sequence, why its effective surface temperature was approximately what in Kelvin? Note that this is requiring you to remember what its current TEF is. What's the sun's current TEF? It's about
5,700.
Yeah, about 5,800, the book quotes, I think, 5777, right? But we should say 5800. So when it hit the ZAMs, it was more like 5500 Kelvin. So the sun is slowly getting brighter and larger even while on the main sequence. Eventually, and it's difficult to say exactly when because of the complexities of modeling the response of Earth's atmosphere to this, eventually, it's estimated between 200 million and 1 billion years from now, Earth will become Venus-like as a result. And if you know anything about Venus, it's got a almost pure carbon dioxide atmosphere. It's got some nitrogen in there too, but it's mostly CO2 at a pressure at the surface of about 90 times that of Earth. So it has a very thick carbon dioxide atmosphere. You probably know that carbon dioxide is a greenhouse gas, and so Venus has an extremely powerful greenhouse effect. Its air is thick enough that you could strap on wings and fly because it's so thick. You wouldn't enjoy it because it is hotter than a pizza oven, and that kind of pressure would very quickly crush you. But if only you could survive the pressure and temperature, you could put on wings and be Icarus and fly around in the Venusian atmosphere. If you think about it, penguins fly, it's just they're doing it underwater, right? They're in a medium that's dense enough for them to essentially fly, if you will. Well, the Venusian atmosphere is dense enough that you could fly if you're on Venus, except for the part of and dying quickly, you know. But other than that, you could fly if you were on Venus. Earth's fate is to become another Venus. So, why is that? Well, first let's talk about the greenhouse effect in general, because it's an application of our understanding of radiative transfer and convective energy transport. They both play a role. I think that's cool. So let's talk about the greenhouse effect. So the very badly named greenhouse effect, because greenhouses do not work via the greenhouse effect. An actual greenhouse does not use what we call the greenhouse effect to be warm. But there's even some physicists who are misunderstanding it, which I think is how there's this myth that the way a greenhouse works is that glass is transparent to visible light but opaque to infrared light. So the stuff inside the greenhouse heats up, gives off infrared light, which is trapped by the glass, and that makes the greenhouse warmer. And that is wrong. That's not how a greenhouse works. A greenhouse works by suppressing convection, by keeping air trapped in it so that it cannot rise and get away. But anyway, a greenhouse gas, badly named, is a gas that is transparent to visible light but is opaque to infrared radiation. Greenhouse gases in the atmosphere of a planet make it warmer than it would be if it had no atmosphere. A planet with no atmosphere has only one source of radiant energy shining down upon its surface, namely the sun. Meanwhile, the sun's going to warm the surface of the planet. Interior heat escaping from the inside of the planet also produces some warming of the surface. And suppose there's no atmosphere. Planet's surface emits primarily infrared radiation because it's not hot enough to give off visible light. So it's mostly IR, just like your body gives off mostly IR. If there's no atmosphere, this radiation escapes directly into space. And you would reach equilibrium, and I think I've given you problems that have this before in it. You'd reach equilibrium when the rate at which energy is escaping into space from the planet's surface is equal to the rate at which the surface is absorbing energy from the sun. When those two things are in balance, you'd be in equilibrium. There'd be no reason for the planet to heat up or cool down. And so that would be the equilibrium there. You'd set, like, you know, sigma t to the fourth power is equal to the rate at which energy is coming in from the sun in order to get a rough estimate of what the surface temperature would be. You might account for the albedo of the surface, the fraction of the sun's light that it just reflects back into space, because what's really important is the fraction that is being absorbed. So it would really be 1 minus the albedo times sigma t to the fourth power would be equal to the rate at which energy's been given off by the sigma. Well, I shouldn't say that. 1 minus the albedo times the solar insolation, the average flux from the sun, would be equal to the rate at which the surface is emitting energy straight into space. But greenhouse gases in a planet's atmosphere absorb infrared light emitted by the surface, and that efficiently warms the atmosphere. Now, that does not mean, so there's another thing, right? The greenhouse effect is notorious for being explained incorrectly. People say, so Earth's atmosphere acts like a blanket. That is not what is happening. Earth's atmosphere is not acting like a blanket. That is not how a blanket warms you. A blanket warms you the same way that a greenhouse works, trapping warm air next to your body. If you're lying in bed and you don't have a blanket on, your body heats the air next to it. What is that air going to do as a result of that? It's going to rise. It's going to rise because it gets heated, it expands, becomes less dense than its surroundings, and it rises. Can that just leave a vacuum behind? You're just sitting there in a vacuum because that air rose? No, of course not. Cooler air from the surroundings will come in to replace it. And congratulations, you will be a radiator. You will set up a convection cell in the room where your body's acting like the radiator. And that will be transporting heat from your body to the rest of the room. And this is not what you want if your goal is to stay warm. So how does a blanket work? You put a blanket on and it keeps that air from rising. It traps it next to you. So blankets fundamentally work by suppressing convection. They keep air from convecting away from you. They suppress convection. That's not how the greenhouse effect works. The greenhouse effect is not because of the suppression of convection. What happens is the air gets warm, and so therefore it's emitting its own thermal radiation in the infrared, because anything that's hot emits radiation, right? Thermal radiation. So at the surface of the planet, there are two sources of radiant heat. Radiant energy shining down upon the surface, the sun and the warm atmosphere. And the result is that the surface reaches a higher temperature than it would if only the sun were shining down upon it. So this is what I would call the astronomy 110 level explanation of the greenhouse effect. We'll do the astronomy 311 explanation in a minute when I show you this video that goes into a more mathy explanation, and in fact we'll present that one layer atmosphere that we were talking about this morning. So, but I do want you to understand this idea here, right? So this I feel is the best explanation for how the greenhouse effect works, kind of without math, just kind of qualitatively. And in fact, if you are standing at sea level in the middle of the day on Earth, it's surprising, but you get about twice as much radiation shining down upon you from the atmosphere as you do from the sun. The atmosphere is the primary source of radiation shining down upon the surface under the conditions of Earth's percentage of greenhouse gases, CO2. So CO2 is a greenhouse gas. What's another greenhouse gas? Do you know? There's another very important greenhouse gas in Earth's atmosphere. What's that?
Methane.
Methane's important, and then there's also another one that's by far the most abundant greenhouse gas in our atmosphere. Water vapor is also a strong greenhouse gas. So methane, water vapor, and CO2, carbon dioxide, are greenhouse gases in our atmosphere. And their effects put together at sea level, you get about twice as much infrared radiation from the atmosphere as you do directly from the sun on a sunny day. In other words, it's really important. The greenhouse effect is our friend. Without the greenhouse effect, Earth would be too cold to live on. So the greenhouse effect is not our enemy, it is our friend. But friends can overstay their welcome, right, so to speak. Global warming, climate change, it's too much of a good thing, is what it comes down to. But this is kind of the big picture of what's going on. What questions do you have so far? Okay, I forgot that I should roll out the speakers in order to play the video. And I'm also, just like I did last time, I actually cut the video about the wow signal out of the video because I don't want a copyright strike from YouTube or whatever. So I'm going to do the same thing here. So hello, audience at home. I'll put a link on the description of this video so that you can play the video in question and then come back to this video afterwards. And it's better that way anyway, because you'll see the video better if you're watching it on your computer directly than on the screen here. So I'm going to go pause this video so that we can actually watch this lovely video from 60 Symbols. Professor Merrifield from, I think it's the University of Nottingham, does a wonderful job of explaining at an appropriate level for astrophysics